By now we have solved the Poisson equation, that is heat conduction in a nuclear rod. And even if you have not solved it yet, now you have some idea that what kind of solution we are going to get. Now the question is our solution acceptable? Is that of acceptable accuracy? Is it useful? Now this is a very important question in numerical simulation, because simulation, the goal of all simulation is prediction. And based on prediction, we take actions. So for instance, if we predict that there will be heavy rain tomorrow, then government might alert emergency services, police and other agencies, and that costs effort and money and human resources. So if our prediction is wrong, then it's a huge loss to everybody. How do we make sure that our prediction is correct? There is no way to exactly match, because there will be rain tomorrow or not, we cannot say right now. So in this case, we have solved a nuclear rod problem. It's a complex problem, but our model is super simple. So the first question we have to ask, that is our model correct? Or is our model correctly incorporate all the variables we are interested about? Does it correctly represent the physical phenomena we are interested about? We are not interested about everything about the nuclear rod. The nuclear rod may develop a thermal stress inside. We are not modeling for that. So the variables we are interested about, are we bringing them together properly? Then the second question is that we have many assumptions, such as constant thermal properties, constant heat transfer coefficient, constant heat generation, and many more in this case. Are these assumptions all right? Are these assumptions good enough so that even after this assumption, the results that we are going to get will match the physical phenomena? Now, these questions here we cannot really answer at this point, because answering this question requires actual data, physical data, experimental data, data from the actual phenomena where it is happening. And in this particular case, we do not have that now. But for certain problem you may be solving, for which if you have data, then you have to try to match with that. Now this is only the part of our question, that is our model correct. The second question is that, is our simulation correct? We are simulating this equation with this boundary condition. But is our simulation correct? And how do you know our simulation result is correct as per this model? Here we are not asking if the model represents the physical phenomena properly or not. We are asking that the solution that we are making, is that a solution of these equations and boundary conditions? Here the question is not about I have correctly written the computer program or not. Assuming that I have correctly written everything, at the end what solution I am getting, is that solution a right solution or not? Now, we are never sure. The problem is that in numerical simulation, you don't know that you are doing it correct. So anybody, you see that he is super confident about his numerical simulation and believes that he knows that what he did is correct. It is only the belief, because nobody knows if it is correct. The only way to know that we are correct, that when we have analytical solution of the same problem available. Now here the issue is that we don't have analytical solution. If we have analytical solution, then we don't need numerical solution. So we are doing numerical solution of certain problem means that we do not have analytical solution. This is almost in all cases, unless you are doing numerical simulation, only to learn numerical simulation. For all practical purpose, wherever we do numerical simulation for certain problems, when we don't have analytical solution. So now, all we can be are that reasonably confident about our solver. We will say that, yeah, we hope that our solver is doing it right, but our hope is not arbitrary. Our hope is based on certain objective information. So what is that objective information? This is the most useful part of this lecture, that what you can reasonably do to be more confident that we are doing the right solution. The first thing that we do is that we verify our solution with certain benchmark problems of similar level of complexity. So if I am solving this is my actual problem, and I assume that there is no analytical solution for this, then we have to solve problems which are close to this and for which the benchmark solution is available. Now, the benchmark problems may have analytical solution or may have numerical solution which is well accepted by the community that yes, that numerical solution is correct. So then we can match our solution with benchmark problems. And the problems is the keyword here. This is not one. We have to match with as many as we can to be more confident about our solver. In this case, the analytical solution is a near impossibility. So we have to figure out what is the close benchmark problems that we can get. Now, for example, one of the benchmark problem could be this solution of Laplace equation. Laplace equation and Poisson equation, they are very similar. Laplace equation is homogeneous. We have 0 here. In Poisson equation, this will be non-zero on right hand side. Now, Laplace equation, depending on the boundary condition, there are many analytical solutions available. Your boundary condition has to be compatible, means that you have 3 homogeneous, 1 non-homogeneous boundary condition. Then you can have analytical solution. And then you can combine many such solution to bring more general cases where you do not have non-homogeneous boundaries on 3 sides. In fact, you can have non-homogeneous boundaries on 4 sides. You can still have analytical solution taking one boundary at a time. So for instance, in this case, let us say this f1x, g1x, f2x and g2x all are non-homogeneous conditions. So you can make 3 of them homogeneous and 1 non-homogeneous. You solve them, you repeat it 4 times and then you add the solution. Then you can get a complete solution. This process works because of linearity. This is called linear superposition. So in this case, with this given boundary condition, the analytical solution will look like this. I have this theta with these 4 terms. All are sine hyperbolic multiplied by sine. And then I have 4 constants, this a, n, b, n, c, and d, n. And these constants can be found out from these integrals. Now this looks pretty intimidating, but you don't have to take all non-homogeneity at the same time. You can pick one by one, have this solution, and then match with your PDE solver, numerical solver. So this is one benchmark problem. Not that this is the only benchmark problem, or this is the, I'm not also claiming this is the best benchmark problem. Actually, similar to this, we should match with several benchmark problems. Then we will be reasonably sure that, yeah, if our solution matches, we're reasonably sure that our solver is doing good. The second part is that our solution must be independent of grid sizes, because this delta x, delta y, etc. or these grids, and in unsteady case, we are also taking this time step. So our solution must be independent of this delta x, delta y, and if time step exists, then time step as well. Because all these delta x, delta y, etc. are artificial constructs. They do not appear in the physical problem itself. We have brought them up to make it possible to have a numerical solution. So at the end, our solution should not depend on delta x and delta y. And this is the kind of investigation that we do to make sure that this actually happens. Is something we call grid independent study. The idea here is that we start with some grid size delta x, delta y, and then repeat with delta x by 2, delta y by 2. So it will double the number of grid points. And this, after this doubling grid points, we check these results with these results. And we keep on doing this until we are satisfied that no more reduction of grid size is necessary. That is where we believe that solution has reached grid independence. In the truest sense, there will be always certain small changes as I go from delta x, delta y to delta x by 2, delta y by 2. But the point here that is this difference acceptable? In numerical solution, we are always looking for acceptable solution, not the correct solution. So when this difference is small enough and we think that, well, we can accept this, then that is our grid independent solution. So there is no objective definition of grid independent solution. It is based on us, based on the requirement of the problem, what kind of accuracy we need. Based on that, we have to decide when the solution had reached grid independence. Finally, we have to match results. We have to verify with benchmark solution. We have to check for grid independence. When we will match result with our benchmark, we will match in the worst possible parts of the domain, not everywhere in the domain. We will match quantitatively. Just qualitative matching, they look same, is not good enough. We have already done quantitative matching. You have seen in case of one-dimensional and transient heat conduction, we have done quantitative matching with analytical solution. So similarly, you have to do quantitative matching on the portions where you expect that there will be a chance of mismatch. So usually that happens near boundary, near large heat sources, etc. Those are the worst places where you match your solution, and all these activities will give us certain confidence about our solver. Still, we cannot say that our solver is the best or even our solver is always correct. We at least know that, yeah, it's very likely that our solver will give correct result. Then based on our solver, someone can take decisions for tomorrow. So to summarize, the first thing about numerical simulation is that we are never sure. This is the key phrase. You are never sure about your solution. Always you have to doubt yourself and you have to keep on checking your solution all the time. Whenever you encounter a new problem, you try to solve it and see how your solver works. So we have to keep on validating, keep on verifying our model as well as the solver. And we have to improve them continuously. And second point, that which we have already said, that it requires quantitative matching. It's not just qualitative. Now in this case, you verify your solver with this benchmark problem here. 2 of the boundaries you can keep at 0 and 2 other boundaries you keep at 1. Then you should be able to run this case in the numerical solver. It's easy. And then you match the temperature profile, not only the contour. Contours give you only the qualitative matching, but profiles will give you quantitative matching. This is a good exercise, and knowing this exercise is very important in numerical simulation. Thank you. That's all for this lecture, and I'll see you in next class.